Welcome to using a table of Laplace transforms. So the general idea here is to take the Laplace transform to take the Laplace transform of familiar functions we can see if it takes the form of one of the functions or one of the families of functions in the table of Laplace transforms. And then if so, we can just use the table instead of evaluating the integral. So for example, let's go ahead and use the table to find the Laplace transform of e to the 2t times cosine of 3t. So I can already tell you that in a Laplace table, we will find this takes the form e to the lambda t times cosine of omega t. This is a form that we will be able to find in the Laplace transform table. So I'm going to go ahead and switch over to the table and we'll figure out what exactly we should use for our transform. So here's our Laplace transform table. We are looking for e to the lambda t times cosine of omega t. And here we have it. So I'm going to go ahead and just transfer this particular line over to our notes. Well, again, using our table, we have our f of t column. We had e to the lambda t cosine of omega t. And then for a capital F of s equals the Laplace transform of lowercase f of t. We get s minus lambda all divided by s minus lambda in parentheses squared plus omega squared, all of that in the denominator. And this is defined for s greater than lambda. So in our case, for e to the 2t cosine of 3t, we are using lambda has been replaced with 2 and omega has been replaced with 3. So we get then that our capital F of s, which is the Laplace transform of lowercase f of t, should be equal to, we would do s minus lambda over s minus lambda in parentheses squared, and then plus omega squared still in the denominator, for s greater than lambda. And if we plug in our 2 and 3, we have that this is s minus 2 divided by, in parentheses, s minus 2 squared plus 3 squared, again defined for s greater than 2. That was our lambda. So this is using the Laplace transform table to quickly evaluate the Laplace transform of e to the 2t cosine of 3t without having to do the improper integral. Let's go ahead and do one more example. Let's use the table to find the Laplace transform of t cubed times e to the negative 2t times sine of 5t. So we have e to the negative 2t times sine of 5t takes the form e to the lambda t times sine of omega t. But then we have times t cubed. So this is essentially t to the k times e to the lambda t sine of omega t. So we are here going to need two pieces. So we will use t to the k times f of t, where it will take our e to the lambda t sine omega t as our f of t then. So this will take a few layers. Let's go ahead and find the relevant information in our table. So our relevant lines, we have an e to the lambda t, sine of omega t is a relevant line. And then another relevant line is our t to the k times f of t. So we will need both of those in order to evaluate our Laplace transform with using the table, not using the improper integral definition. I'm going to go ahead and transfer those two lines over to our notes. Again, here we have our two relevant lines. So we are going to do, for using this first line, t to the k times f of t, we are viewing k equal to 3 since we are doing t cubed. And then in this case, our f of t, which is different from the f of t we started with, is going to be that e to the negative 2t sine of 5t. So we know that if we have t to the k times f of t, that the Laplace transform would go to negative 1 to the k. So in this case, we will have a negative 1 cubed. And then we are going to multiply by the third derivative of the Laplace transform of that new f of t, that e to the negative 2t sine of 5t. So we are going to multiply by the third derivative of capital F, where capital F of S is the Laplace transform of e to the negative 2t times sine of 5t. Having done that, we now need to know what is the Laplace transform of e to the negative 2t times sine of 5t. And in order to do that, oops. Sorry about that. I didn't expect everything to move, including the writing. All right. So in order for us to find that Laplace transform, we will now use e to the lambda t sine of omega t. So here we have our lambda is negative 2, omega is 5, and we're looking at e to the negative 2t sine of 5t. So that will go to this f of s that we were looking at. So the Laplace transform of e to the negative 2t sine of 5t should be equal to, we do omega divided by s minus lambda squared plus omega squared, defined for s greater than lambda. Here our, again, lambda was negative 2, our omega was 5. So we are looking at 5 divided by s minus negative 2, or s plus 2 squared plus 5 squared, looking at s greater than negative 2. So now we need to find the third derivative of that. So this is our capital F of S. This is, I'm putting it in quotes. This is not the one we originally wanted. So to find now our Laplace transform of t cubed e to the negative 2t sine of 5t. This is negative 1 cubed times the third derivative of that 5 over s plus 2 squared plus 5 squared. This is not a derivative I particularly want to take at the moment, so I'm just leaving that as the third derivative of 5 over s plus 2 squared plus 5 squared. Again, looking here at s greater than negative 2. So this is how we would go about finding something where we kind of need to use the transformations and familiar functions from the Laplace table. This is how we can use the Laplace table to avoid having to use those improper integrals. Again, this one's maybe not the most pleasant since we are taking the third derivative of a rational function. And so I'm going to stop here, but that would this is how we would go about applying that table.